Well, let me start. In the mid-80s, there were 3 surprising discoveries about the structure of matter and its properties. And these, thank you so much. And the green one. They came year after year. The first one was 1984. This is our discovery, Quasi Periodic Crystals. And the name of the publication is Shechtman, Blech, Gartias, and John Kahn. In fact, the discovery was made a couple of years before that, 1982, as I will show you, but the publication came in 1984. Next came fullerenes, 1985, and then high temperature superconductivity. And by now I can say that all 3 of them got the Nobel. They were discovered year after year, one after the other. Now, there was a surprise. Let's start from the last discovery, high temperature superconductivity. Superconductivity was discovered early in the previous century, and it was nicely explained. And so when high temperature superconductivity was discovered, the surprise was that there is superconductivity at high temperature, not that there is superconductivity, but there was no objection. It was nicely received, and people saw applications when you can move from liquid helium to liquid nitrogen. It's cheaper, it can be useful, and indeed in MRI, high temperature superconductors are used today. When fullerenes came, well, this was another way in which carbon atoms can form. And so there were buckyballs and then nanotubes and other forms. And last year, Nobel Prize in Physics was on graphene, which is a flat form of carbon, and it has special electrical properties, as you well know. But there was no objection to the finding. The discovery of quasi-periodic crystals was met with great skepticism and objection, as I will tell you later on. And this is because there was a need for a paradigm shift in the science of crystallography in order to accept the new form of matter. Before I start, let's just say a few words about order, about periodicity, and about rotational symmetry, so that everybody, and I'm talking to the students mainly, everybody is with us. So what we have here is an ordered array of atoms, a square array of atoms, and clearly there is order in this array. Now let's say a word about periodicity. If you go along this line, you realize that there is periodicity, and if I ask you to continue to put atoms along this line, you know exactly where to put them because you understand what the periodicity is. And you can do that in each and every direction. Anytime you connect 2 atoms, you connect an infinite number of atoms in the crystal. So this is order and periodicity. Now what about rotational symmetry? We can rotate the crystal, and we can rotate it, in this case, as you will see when I add a handle to it, I rotate it, and I can rotate it 4 times until it comes back to its original position. Anytime I rotate it, you will not be able to see that I have done anything to it, except for the handle that is there. So this has a 4-fold rotational symmetry. And an image has a rotational symmetry if there is a center point around which an object is turned a certain number of degrees, and the object still looks the same. That is, it measures itself a number of times while it is being rotated. And here we have a few more examples of rotational symmetry. We have a 2-fold. The card is a 2-fold rotational symmetry, and 3-fold here, and 5-fold here, and 7-fold here. This pizza is a 6-fold, and so on. So these are the terms. Let's say a couple words about crystallography. The science of crystallography really, the modern science of crystallography really started in 1912 by the seminal experiment by von Laue, a German scientist, who showed in one experiment 2 very important things. He showed that X-rays have wavy nature, and he showed that crystals are ordered, as people thought before. Now, bear in mind that X-rays were discovered in 1895 by Röntgen, and for 17 years, nobody knew what they were. People used them a year after the discovery, but only in 1912 did von Laue show what they were. So he started really the science of modern crystallography. Now, bear in mind, there was crystallography before. The mathematics was there, and everything was already there, but experimental crystallography did not exist except among the geologists who measured angles between facets of crystal that they have found in nature or that they have created in the laboratory. And by measuring the angles, they thought they could understand what is the arrangement of atoms in the structure. When X-ray were discovered, when X-ray diffraction became a tool, the X-ray crystallographers said the following: we are the precision people. We can measure exactly distances between atomic planes and so on. And so we are not like these geologists, we are X-ray crystallographers, unlike what was there before. This, in turn, created a situation in which X-ray crystallography not only did not accept results from before, they did not accept results from after that, when electron microscopy and electron diffraction came into the game. They said no, as I will show you later on. Okay, a crystal definition until 1991. A crystal can be defined as a solid composed of atoms arranged in a pattern periodic in 3 dimensions. This is from X-ray diffraction by quality, which is a book that we were using when I was a student. It's an excellent book. So periodicity and order is synonym. Second definition: atoms in crystals are arranged in a pattern that repeats itself in 3 dimensions throughout the interior of the crystal. Same definition, basically, different words. Order is periodicity. This was crystal. Crystallography in 1982, I can give you an example of a book that we all studied from, Charles Kittel, Introduction to Solid State Physics. I marked there by a green line a sentence I want you to read, but I know you cannot do it now, but maybe you can do it now. So it says the following: we can make a crystal for molecules which individually, each one of them, have a 5-fold rotation axis, each one. But we should not expect the lattice to have a 5-fold rotation axis. Okay, everything was nice and clear. And when we looked at the real space by electron microscopy, this is how atoms in a crystal look like. Each white dot is an atom in diamond in this case. These are carbon atoms arranged in a pattern which is ordered and periodic. So you can see the order and periodicity. And this is in one orientation. If you look in different orientations, you'll see different order. But the order is there, and it was always periodic. So this is the real space. Now let's look at the reciprocal space, the diffraction pattern. Here is a diffraction pattern. This is an electron diffraction pattern. And these dots are not atoms. These are diffraction spots taken by an electron microscope. And the rules that exist in the real space exist also in the reciprocal space. Namely, there is periodicity in the diffraction peaks in the reciprocal space. The rotational symmetries that are allowed in periodic pattern are 1, 2, 3, 4, and 6, no 5, and nothing beyond 6. So these were the rules for many years, from 1912 until 1992. In 1992, a new definition of a crystal has emerged. And this definition was created by a committee nominated by the International Union of Crystallography. And the definition says the following: by crystal we mean any solid having an essentially discrete diffraction diagram, And by aperiodic crystal, we mean any crystal in which three-dimensional lattice periodicity can be considered to be absent. Now look at this definition, how beautiful it is. And it is very beautiful because it's a very modest, soft definition. Probably the most soft definition in science. Because it doesn't say a crystal is. It says by crystal we mean any solid having, it doesn't say any solid having discrete diffraction diagram. No, an essentially discrete diffraction diagram. Very, very soft. And so on and so forth. This humble definition is wonderful because of several reasons. Number one, a humble scientist, in my opinion, is a very good scientist, one who is open to new discoveries. Number two, it came from the International Union of Crystallography, which was extremely, but extremely strict up until 1987, and I will tell you what happened in 1987. Well, very, very strict. And from them to arrive at such soft, humble definition, this is a great achievement for the International Union of Crystallography. In 1982 was the 70th birth of crystallography, 70 years after 1912. And this was the year that quasi-periodic crystals were discovered. And to see what happened then, I will show you a page from my logbook. This is a TEM logbook, Transmission Electron Microscope logbook. The place was NBS in Maryland, United States, National Bureau of Standards. Now it's called NIST, National Institute of Standards and Technology. And here it is. Now, this page was never meant to be seen by anybody but me. These are notes written for me just to remember what did I do, when, and why. And it is written in the dark. When you sit in an electron microscope, what you really want is no light at all. Any LED in the far corner of the room is a great disturbance. You don't want that. Usually people put pages on it, books. So you really write in the dark. Now, let's see what it says. Up here you see the date. It's April 8, 1982. And the alloy that I have studied is aluminum 25 weight% manganese. And this is plate number 1720, and so on. So you can imagine, as you can see in the book, I've done quite a few experiments before that. And then SAD, it doesn't mean that I was sad that day, it only means that it is selected area diffraction pattern. Selected area diffraction pattern, and then 28K means magnification. This is a bright field image with 28,000 magnification, which is a low magnification for a transmission like microscope. If you don't need very high resolution, you can magnify only a small amount like this, and so on and so forth. And then this plate, number 1724, 36K, and then I saw something very interesting, and what I saw I will show you in a minute. What I saw were crystals in the specimen that were extremely dark. When you see a crystal which is extremely dark, either you do not know how to prepare a specimen for the electron microscope and it's so thick that the beam doesn't penetrate, but that's not me. Another reason could be that that crystal diffracts heavily. So the transmitted beam has very low intensity. And consequently, if you form the image with the transmitted beam, you see it's very dark because all the beams are diffracted and stopped by the objective aperture. Only one beam goes through. And then I said, wow, that's interesting. Let's look at the diffraction pattern. And I will show you soon the diffraction pattern. Select the diffraction tenfold. That's odd. So let's go and see first the crystal. And as you can see here, some of them are very, very black, very dark. This here and this here. While others, these are transparent, more or less. Right? This is normal view, but that's very abnormal, dark like this, heavily diffracting. And this was the electron diffraction. So when I saw this electron diffraction, I remember very well. I was sitting there and saying, wow, that's very odd. And I started to count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No, cannot be. The other way. 1, 2, 3, 4. Tenfold, and this is why I wrote tenfold. And then I thought that I knew what it was, as I will explain you shortly. And I performed a series of experiments, which you can see in my logbook. One more. Yep. So you can see all these experiments, which are linked by this chain, are done on one crystal. This is a note for me that this is one crystal. And I took a series of dark field images, as I have noted myself here. And the dark field image it does the following. Let me explain a little bit about electron microscopy. In an electron microscope, you have a specimen which is transparent, and the beam penetrates through. This is why it's called transmission electron microscope. And under the specimen, the beam, part of the beam goes through and part diffracts. And there is an aperture there called the objective aperture. And you can, let's say that all these are diffracted beams, and this one here is a transmitted beam. And there are many of them. So if I let the transmitted beam go through and form an image with a transmitted beam, we call it bright field image. Transmitted beam, bright field image. But then you can tilt the beam so that one diffracted beam will go through. And then if you form an image, it's called dark field image. Now, if you form a dark field image, then the image which you see, the bright part of the image, is the part that contributed to that diffracted beam. Okay? So the thought was that what I have there are twins. Twins are defects in a crystal. And I can explain it with my hands briefly. Let's say that you have a crystal here and another one here. And usually if the orientation is just any orientation, then you have a grain boundary or a crystal boundary. But sometimes you have very special orientations. They look like a mirror image, like that. And then we call them twins, and this is a twin boundary. Twin boundary is a regular grain boundary or crystal boundary, but very specific orientation. And what I thought was that what I have there is a series of five-fold twins. That means that I have 5 twins arranged 72 degrees to each other. And really, the diffraction pattern is a composition of 5 diffraction patterns superimposed on each other. That was my thought. Why did I think so? Because I had previous experience with crystals that behave just like that. And so all these experiments were performed in order to find the twins. See, this is a series. Yeah, watch that. This is a series of dark field images that were designed to find the twins. And I could not find them. They were not twins. And then I said, okay, let's do another experiment. Another experiment that you can do by transmission electron microscope is you can converge your electron beam onto a small spot on the specimen, make it as small as you can, and then take a diffraction pattern from that very small spot. And if there are twins, which are larger than that spot, then the diffraction pattern should be from a periodic simple crystal. And when you move the beam to another one, you'll see another one, and another one, and another one. That didn't happen. So in day one, I knew that there were no twins in this material, and it was a mystery for a while. So not only was the 5-fold or 10-fold, by the way, it's really 5-fold, but I could not tell that by the diffraction pattern. There was a need for another experiment to see that it's really 5-fold. This is why I wrote 10-fold. So not only there was not only one axis of a 5-fold diffraction pattern. There was 5, 2, 5 in this direction. And in that direction, there was 5, 3, 2, and 3. Moreover, if you go back for a second and look at this diffraction pattern, if you look for the periodicity, it's not there. If you go along one line and you take any distance, say from the center to this spot, and you multiply it by an integer, say 2, you arrive here, and there is no spot there. So there is no periodicity. Tenfold, no twins, no periodicity. That's interesting. Now, when I was a student and I did my master's degree here at the Technion, in the Department of Materials Engineering, as it is called now, I took an exam in crystallography. Shmuel Nadiv was a teacher. And he gave us, in the exam, a question, prove that 5-fold rotational symmetry cannot exist in crystals. And I proved it. and I passed the exam. And this is one of the reasons I can be here now. So let me show you how you can show that 5-fold rotational symmetry does not exist in crystal, in periodic crystal, that is. Now, take two atoms, P and Q, such as this and this, and choose the two atoms that are the closest together. So R is the minimum distance in that crystal between two atoms. Okay? And if 5-fold rotational symmetry does exist, then you should be able to rotate Q around P 5 times and P around Q 5 times. And let's see what happens when you do that. So let's rotate Q around P. So we are here, and here, and here, and here, and here, 5 times. And there should be an atom here at Q prime. Q prime, there should be an atom here. And then let's do it for P around Q. So here is P, 2, 3, 4, and 5. And there is P prime. And because of geometrical reasons, Q prime, P prime is closer than PQ, and I chose the closest atoms in the structure, so that cannot be, no 5-fold rotational symmetry. However, there is a pseudo 5-fold rotational symmetry, as I told you, with twins. And here is an example. This is a micrograph that I took many years before the discovery, somewhere in the 70s. And it was so trivial that I never published it. Later on, I discovered that one Chinese crystallographer published about 5 papers on this picture. There was nothing to it, but some people can do that. Okay, so what we have here is a crystal which is found in the aluminum iron system, and you don't have to do anything special. Just cast an aluminum iron composition, and it appears in many compositions. And large crystals like this grow. You can see them in an optical microscope. They are large. So here is one in the transmission electron microscope, which is quite nice. What you see here are 10 crystals, and but they are twin related. That means that this crystal is twin related to this, and this is twin related to this, and this is twin related to this, and so on. And in between each two, you have a twin boundary. Now, if you take a diffraction pattern from one of them, then you have a regular periodic diffraction pattern. But if you take a diffraction pattern from all of them together, then you have 10 superimposed diffraction patterns, 36 degrees from each other, and this superposition has a 10-fold rotational symmetry, of course. And this is how it looks like. And this diffraction pattern was taken from the crystal that I've just shown you when I took a diffraction pattern from all of them together. And this has, seemingly, a 10-fold rotational symmetry. But in fact, we know that these are indeed 10 twins, and you can take the diffraction pattern, as I had, from each individual one, and you can show that that is something like this. Each individual one will look like that. And you have 10 of them that form the whole. In fact, if you do that, you have 5 of them, but let me tell you why. Because 2 twins which are opposite to each other like that have exactly the same orientation. So we have 2 like this, 2 like this, 2 like this. Altogether, 10 twins, but 5 diffraction patterns superimposed. Okay, so this is what I had in mind when I did this experiment. Later, in later years, this is long after discovery, I found also 5-fold twins in diamond. These are this is a high-resolution micrograph of atoms in diamond. And this is not exactly five-fold twins because they are of two kinds. And we are not going to go into sigma notations now, but I have here 4 sigma-3 twins and 1 sigma-81 twin. And this was a study that I did publish later on. So five-fold twins exist. It's not extremely rare. The dark field experiments that I did are seen here. These are the real pictures. And as you can see, I used this diffraction spot to take this image, and use this diffraction spot to take this image, and this to take this, and this to take that. And there were no twins. I couldn't find any twins in any orientation, in different orientations here. So this was number 1. And the other experiment was microdiffraction, and here are one of the experiments, microdiffraction. And the expectation was that if there are twins, and I have a very small beam of electrons impinging on the specimen, then when I move the specimen under the beam, I should have periodic like this, periodic like this, periodic like this. Didn't happen. No twins. Why am I expressing this? Because in later years, the last objection to quasi-periodic materials was that by Linus Pauling, as I will describe, then he said that these are really twins in a periodic crystal, which I knew from day one they were not. Here's another experiment. I didn't do that. This is high-resolution microscopy. My friends in France did that. And this is a very interesting experiment. You see, this is a lattice image, and this is a diffraction pattern. OK, nothing new now. But what you can do now, as my friends did, they took this image and put it on a small slide and had a laser beam go through it and had an optical diffraction. Professor Lipson is here, world expert in optical diffractions. And the optical diffraction looks like that. So you say, OK, big deal. They look the same, of course, because both are Fourier transforms of the image. One in the electron microscope and one by optics, laser beam. They should look the same. So what's the big deal? Well, the big deal is that you can shine the laser beam on a small spot there on your specimen and look at this diffraction pattern. Of course, now you can do it on the computer. You don't need a real laser to do that. But at the time, we didn't have FFTs and so on. And so when you have this aperture, you can make it smaller and smaller and smaller. And as it gets smaller and smaller, this image will not change. It will disappear for lack of information, but it doesn't change. OK, final proof that really there are no twins there. Today's images are nicer than at that time. We have much better microscopes. And of course, they cost much more money. We have one that costs $4.5 million in our department. I just visited the newest electron microscope in Gothenburg in Sweden. Their cost $6.5 million. So as you see better and better, and the resolution there is about 0.6 or 0.65 angstroms. By the way, electron microscopes today, you don't sit by the microscope anymore. The microscope in another room, you have a console wherever you want. In the next room, in the next continent, wherever you want, and you work the microscope. Somebody has to put a specimen in the microscope, but from there on, you can be on an airplane and work the microscope. OK, so this is a modern sample. OK, 1984, I will tell you what happened in 1984. That year, I returned, actually, back in late 1983, I returned to the Technion from a sabbatical at NBS. I had all these results, but I needed the help of Ilan Blech, who was here, a professor, and Ilan Blech proposed a model that explained how these materials could form, how these diffraction patterns could form. And his model was later known as the icosahedral glass, which were, the model consisted of icosahedra which join in space in arbitrary way, but keep their orientation. And then we wrote a paper, and in 1984, I was back at NBS for the summer, And I sent the paper for publication in Journal of Applied Physics. And it bounced back like a tennis ball from the wall. 1, 2. It was back on my desk with a letter saying that it will not interest the community of physicists. Well, I'm happy it does now. And I should send it really to a metallurgical journal, which I did. And I sent it to a metallurgical journal. It's called Metallurgical Transactions. They accepted it, published it, but they published it many, many months deep into 1985. In the meantime, I showed my results to my host there, John Kahn, and he proposed to write a shorter paper, much shorter, not including Ilan Blech's model, just the results, and publish a quick one. He invited Denis Gratias, a mathematical crystallographer from France, who joined us, and the four of us sent a short paper to Physical Letters. It was published very quickly, and then it was published November 12, 1984, and then hell broke loose. I mean, the community was overwhelmingly accepting, and especially young physicists, mainly from France, because Denis went back to France to spread the gospel, and in many other countries, Japan, Germany, many countries in the world, China, people started to work on quasi-periodic materials, and then really the new field was created at that time. Let's say a few words about icosahedral symmetry, which is the symmetry of the icosahedral phase. This is why I named it icosahedral phase. This is an icosahedron, and an icosahedron has 6 5-fold axes. 5-fold meaning that if you look from this spot to the center, you'll have a 5-fold rotation symmetry. If you look from this spot where you view it now, clearly it has 3-fold rotation symmetry. And if you look from the center of one of the bars into the center, from here to here, you have a 2-fold rotation symmetry. So this is the icosahedron, and you can better understand it if you look at a football, and you see 5-fold rotation symmetry, 3-fold and 2-fold, and the football has an icosahedral symmetry. Of course, every football player knows that, right? Okay. Now, let me tell you the story of what really happened. From 1982 to 1984, I was alone in the laboratory, and I was rejected to a certain extent. And the local community, the corridors around me, varied between encouragement of John Kahn, for instance, my host, who said something like, Danny, this material is telling us something, and I challenge you to tell us what it is, to total rejection from my group leader, who came to my office one day, smiling sheepishly, putting a book on my desk and saying, Danny, please read this book so that you'll understand that what you're saying cannot be. And I said, you know, I know this book. I'm a teacher at the Technion. It was a book about X-ray crystallography. I'm telling you, this material is not in the book. Took the book, came back later and said, Danny, you're a disgrace to my group. I don't want to be associated with you. Please leave my group. So I left the group. I went and found some other colleague who took me to his group. And it didn't mean much. I didn't have to leave my office or my laboratory. I just had to report to another secretary. So it didn't mean much, but this was the atmosphere between encouragement and total rejection. This was between 1982 to 1984. 1984, I had Ilan Blech, and then John Kahn and Denis Gratias. We were a group, and I was not alone anymore. But during these 2 years, if you want to see how I felt, that's about how I felt during the first 2 years or so, a year and a half or so. And then one anecdote. When the paper was published, and I met again at NBS in 1986. This is about a year and a half after the publication, right? It was published towards the end of 1984. That's about a year and a half. And the month is July. And a colleague of mine wrote this on a piece of paper, and he brought it to lunch. I just took it from him, and I took a picture of that. And what it says is the following. This N is the number of pages in the bibliography. Let's say that each page contains, I don't know, 30 publications or so. So N is the number of pages. Each contains so many publications. This is the bibliography. So let's say that 0.1, meaning 10 pages full of publications. And he drew a line between January to July, and to our horror, it was a straight line. And that meant that in December of 1986, the number of publications will reach infinity. Hey, this is a scientific graph, no? So it didn't happen, and all the trees in the Amazon were saved. Otherwise, they will have to be cut just to provide the paper for all these publications. It didn't happen, but this was the feeling that the world is exploding around us with activity. It was a wonderful feeling, and we had immediately colleagues from around the world. Now, what happened in let's go back for a second. What happened in 1987? 1987, I had the first results of X-ray diffraction. Why couldn't we have X-ray diffraction before? Because the crystals were too small. And if you need to take a diffraction pattern by X-rays from a crystal, you need it to have a certain size. You need to hold it somehow. You have to put it on the tip of something and shine an X-ray beam through it. It has to be a certain size. But not 2 microns, 3 microns. Our crystals were 2, 3 microns. You cannot take a single crystal diffraction pattern. What happens if you take X-ray diffraction pattern for many crystals? Everything is fine and dandy, except that you don't see the rotation symmetry. And the rotation symmetry is the whole thing here. So we needed the large crystals, and friends of mine, both in France and in Japan, that year grew large enough crystals, and those crystals were large enough to take X-ray diffraction, and they sent me the X-ray diffraction. I took those diffractions to the International Union of Crystallography meeting in Perth, Australia. This is on the west coast of Australia, 1997. And when I showed these results to the community, they said, okay, Danny, now you're talking. Now we understand what you're saying. And they formed a committee, and the committee created the new definition of a crystal. And by that, quasi-periodic crystals were accepted to the community of crystals, and as you will see later, it made a difference. Linus Pauling was the last person to object. After 1987, most of the community accepted quasi-periodic materials, but Linus Pauling persisted in not accepting it. Now, it wouldn't be important except for 2 facts. Number one, Linus Pauling was really an eminent scientist, probably the most eminent chemist of the 20th century, or if not one of the most eminent. So he was important. 2-time Nobel Laureate, one in chemistry, the other one in peace. And he was not alone. He was the father of the American Chemical Society. And he had hundreds of thousands of followers. And when Linus Pauling stands there and said that Danny Shechtman is talking nonsense on stages, much louder than this, and there are no quasi-periodic materials, only quasi-scientists, then the crowd said, really, like in a political meeting, or more like in a religious meeting. I mean, everybody was. So he was not alone. He continued to propose larger and larger unit cells that, if twinned, so he said, would create the diffraction pattern that I have seen in the electron microscope. I met him several times. I'll tell you about one of these meetings. By the way, each time we met, we were very nice to each other, and we agreed about everything, vitamin C included, but never agreed about quasi-periodic materials. And in one of our meetings, I went to his office or laboratory or museum, if you wish, in Palo Alto, California, and I gave him a talk for one. There was one person in the audience, and I was there with slides, remember slides in boxes? And I gave him a talk, for 1 hour talk. And at the end of the talk, he was listening there. At the end of the talk, he said, well, Danny, I don't know how you do that. Meaning he didn't know electron microscopy. He didn't understand the power of an electron microscope. He didn't understand how it worked. So if it were somebody else, I would say, well, you know, go read a book if you don't understand what I'm doing. But this was Linus Pauling. He wrote the books. So all I said was, Professor Pauling, if you ever agree with me, don't keep it a secret. Publish it. Okay? He said, well. Okay. That was that. That was the last time I saw him. But then he wrote me a letter. About 1992, he wrote me a letter saying, Professor Shechtman, let us write the Shechtman-Pauling paper on quasi-periodic materials. And you will be first, he said. He wrote, Shechtman-Pauling. And he said, Professor Pauling, I wrote him a letter. You remember letters, envelopes, stamps? Yeah. I wrote him a letter saying, Professor Pauling, I'll be delighted to write this paper with you, but first we have to agree that quasi-periodic materials do exist. He wrote me a letter back saying, well, that may be too early for that. And then a couple years later, 1994, he died, and with him died the resistance. Let me show you a few things that will make you understand better quasi-periodicity. And what I'm showing to you now is called the cut and projection method, and it was presented to me and to several other people in France, in Paris, in the School of Mathematics of Louis Michel, who passed away a few years ago, and who was a great friend of the Department of Physics here, a frequent visitor. He came here every year. And in that meeting, there was a couple of young scientists named Katz and Dunot, and they presented to us something which existed before, but it was pertinent to quasi-periodicity. And let me show you what they did. It's called the cut and projection, and what it means is that you can take a higher dimensional space, which in this higher dimensional space you have a periodic system, such as a two-dimensional space here, and you have a periodic system of dots. Each one meets in the intersection of two lines. There's a mathematical spot dot there. And then what you can do is you can make a cut. A cut meaning you create a strip in that periodic system, and the strip emerges from one unit cell here and goes in a certain direction, not just any direction, but in this case I've chosen the angle alpha to be the Fibonacci number, which is an irrational number. When I do that with an irrational number, all it means is that that line that emerges for one mathematical spot will never meet any other spot ever. Because if it does, then the tangent will be a irrational number. So I send it into an irrational direction. And then this is the cut. And then you can do projection. Projection means that you collect all the spots which are within the cut and project them onto a lower dimensional space, which is a one-dimensional space, which is this line. So you have a cut in a two-dimensional space, and you project on a one-dimensional space, which is this line. And if you look at the distances that are formed by this projection, large, large, small, large, large, small, large, small, large, large, small, and so on, this is exactly Fibonacci series. So here comes Fibonacci, and we'll say a couple of words about Fibonacci later on. And the direction is Fibonacci number, meaning that the tangent of the direction is the Fibonacci number tau, 1 plus root 5 divided by 2, tau or theta or phi, some people call it. Now, let me show you something else. Here are the two lines that I've shown you before going in an irrational direction. But now I take two lines that go into a rational direction, but very, very close to the irrational direction. So the red is a rational direction. How do I know that? Because I made it so that they will meet this spot. Maybe with the arrow it will be better. This spot is met by the red line. And so the ratio, the tangent, is a rational number. This 11 divided by 7. But they're close together. So if by the black lines we have created a quasi-periodic system which was projected onto a lower space. Here we create a periodic system. And because the periodic system, or the periodic array, is very close to the quasi-periodic array, we call them approximant. In real space, approximants are crystals, which structure is very similar, but not quite, very similar to quasi-periodic materials. These are periodic materials that are similar to quasi-periodic materials, and these are called approximants. Okay, now here are the diffraction pattern, the X-ray diffraction patterns that I took to Australia, to Perth, Australia. And these three pictures are the pictures that convince the community. This is X-ray diffraction. This is a Laureate pattern, as we call it. They convince the community that quasi-periodic materials do exist. Here on the left, you have 5-fold rotational symmetry, 3-fold, very nice, very, very pretty, and 2-fold here. Okay, let's say a few words about Fibonacci blockhead of Pisa, as his friends were used to call him. So this is a drawing of him, and this is a statue. The statue exists on his grave, in the graveyard. He's buried behind the inclined tower of Pisa. And there is it's a graveyard under the roof. So if you visit the inclined tower of Pisa, just behind it you can find a graveyard in which Fibonacci is buried. And Fibonacci is famous for very many things, and he was the greatest mathematician of his time. And many hundreds of years later, he was really number one. This is one of his famous experiments or developments, if you want. And it's about the Fibonacci rabbits. And the Fibonacci rabbits multiply according to a certain rule. Let's say that males are not necessary, only females. And now we have a female rabbit on the first month. And she gives birth to a little one on the second month. And on the third month, she gives birth to another little one. And this one has to grow up before she can reproduce. So these are the rules. And it goes on and on and on. And the number of rabbits in each month are marked here. And this is the famous Fibonacci series. 1, 2, 3, 5, 8, 13, 21, and then 34, and so on. And here are the two fundamental rules. And the two fundamental rules of Fibonacci series are that the number of rabbits in each month equals to the number of rabbits in the 2 previous months. This is equation number 1. Equation number 2 says that if you go to the limit, infinite number of rabbits, then the ratio of 1 month, the nth month, to that of n minus 1 is the Fibonacci number, 1 plus root phi divided by 2, which is tau or phi or so. So this is Fibonacci. He published it in the year 1202, early in the 13th century. And this is one of the things he's famous for. This is quasi-periodic system in 1 dimension. 2 dimensions are Penrose tiles. Penrose tiles are a quasi-periodic array in 2 dimensions, and named after Roger Penrose, who is an eminent scientist in England. He lives with us today. And if you forget the colors and you look just at the shapes, then there are only 2 rhombi, a thin rhombus here, thick rhombus here. And if you put them together according to certain matching rules, not just anyway, according to certain matching rules, then it will create a quasi-periodic array in 2 dimensions. In 3 dimensions, you have crystals. This is our space, and this is a crystal of magnesium zinc cerium taken in my laboratory by one of my workers at the time. And you can see it's a beautiful crystal with 5-fold facets. Okay, and here are a couple of nice examples of, this was sent to me by my friend Anpeng Tsai from Tohoku University in Japan. The colors are artificial, but this is a scanning electron microscope picture, like blossom, cherry blossom, if you will. And you see the 5-fold rotation symmetry and the 3-fold, because from here it's 5-fold, and from here 3-fold, and so on. So let me try to sum up. While as before, order was synonym to periodicity, after 1987, the International Union of Crystallography accepted quasi-periodic materials and said that periodicity and quasi-periodicity will belong to the realm of crystals. Not only that, but they made that very soft definition that meant really we are open to new discoveries. Maybe there are more things here that need to be discovered, which is wonderful. Now, before I finish, let me answer a question you did not ask, and later on I will answer questions that you will ask. And the question you didn't ask is why quasi-periodic materials were never discovered before 1982. But before that, I would like to mention a few people who were really contributed the most important contribution to the beginning of the field. And first, I would like to mention Penrose, whose structure you have seen, but also Alan Mackay. Now, Alan Mackay is also a British mathematician who took Penrose tiles and showed that they diffract and they create very sharp spots. So we have a quasi-periodic array with sharp spots. He didn't know about materials that do that, but the mathematics was there. Here is Penrose tiles, here is the Fourier transform, and the Fourier transform has sharp peaks. So this was important, and Penrose published it in the 70s. Mackay published his paper in 1981, just a year before the discovery. I never knew about his experiment. Number two was Ilan Blech, whom I mentioned before, who with me wrote the first paper after he proposed the model that explained how the diffraction patterns could form. Number three are Dov Levine and Paul Steinhardt. Dov Levine is in physics here, Paul Steinhardt is in Princeton. And they published a paper very quickly after our first publication. They took Penrose, Mackay, they took our diffraction pattern and said, this is the same thing, and proposed the quasi-periodic tiling model, which is the ruling mathematical model today. Now, let's go to the question. Why QCs were never discovered before 1982? Is it because they are very rare, so that nobody saw them? Now, bear in mind, let me give you some numbers. For 70 years, 1912, 1982, hundreds of thousands of crystals were studied by eminent scientists who studied their structure very carefully, very, very carefully, and published those structures in endless books and in cards, and it was in the media, it's on the internet you can find all that. And nobody saw quasi-periodic materials, maybe because they are rare and only me with my sheer luck found them. Or maybe they're not stable. You look at them, they transform. Or maybe they're difficult to make. Well, let's see. Are they rare? Not at all. On this list, you see part of the quasi-periodic crystal that exists in the aluminum system. Just one element. All these quasi-periodic crystals exist, and there are more in aluminum. And you can imagine that there are many other elements on which quasicrystals are based. No, that's not the answer. They are abundant. They are found everywhere. Maybe they're not stable. Well, many are indeed not stable, but what does it mean? It means that when you make them, let's say by rapid solidification, which is a commonly available technique, they are stable at room temperature. You have to heat them up to 300, 350, 400 degrees, and then they transform. But at room temperature, stable. And then there are stable quasi-periodic, there are stable quasi-periodic materials that melt congruently without any transformation. So that's not the answer. Maybe they're difficult to make. Not at all. Extremely easy to make them. You can make them by casting. You can make them by rapid solidification, by single crystal growth, by electrodeposition, by CVD, PVD. Any technique that you can produce material, you can produce quasi-periodic crystals. Easy to do. So why is it that quasi-periodic crystals were never discovered before 1982? Now let me give you my answer. You may have other answers. That's, from now on, it's speculation. I think the following. Number one, quasi-periodic materials had to be discovered by TEM, by transmission electron microscope. And this is because they were very small. And if they're not, and if you do X-rays, you see rings and you lose the rotation symmetry. You have to have a single crystal diffraction pattern to see the rotation symmetry. And only TEM could do that. It took years, it took 3 years to grow large enough crystals for X-ray experiments. So you can imagine that this is difficult. They had to be discovered by TEM. This is a great victory for transmission electron microscopy, because when the International Union of Crystallography accepted quasi-periodic materials, they accepted electron microscopy as a legitimate tool, which is wise because it is a wonderful tool. So TEM, that limits the number of scientists to TEM, people who work on TEM. Then you have to be a professional at TEM. What does it mean? It means the following. When somebody is giving a permission to work on the electron microscope, all it means is that the person responsible for the laboratory trusts him not to destroy the microscope. Then he gets a driver's license on the microscope. That doesn't mean that he knows what to do with it, but they trust him that he will not destroy the microscope, which you can easily do if you don't know what to do. But now you have to learn electron microscopy. Take a class in electron microscopy, take courses on how to use the electron microscope, and what you can do with the electron microscope, and work a few years until you become a professional electron microscopist. Most students, the vast majority that use electron microscopes, use it as a magnifying glass, period. They don't use all the capability of the electron microscope. So you have to be a professional. Fine. And then when you discover something which is against the grain of a very established community, you have to have some tenacity, like a Rottweiler. You don't let go. And that's a matter of character. So some people are like that. Other people are not. Let me give you an example. Colleagues of mine in Belgium, in Antwerp, that was a center for electron microscopy, much like Oxford, Cambridge, Antwerp. This was the core of electron microscopy. So a student of Professor Ameling's saw the five-fold rotation symmetry diffraction pattern, took the diffraction pattern years before he saw that. What did he do with it? He filed it. And later on, when he left, years after he left, people found it in the file there. He didn't do anything with it, okay? So, all right, you have to do something with it. And then you have to believe in yourself. And you believe in yourself if you are a professional. And this is what I'm telling a student. If you want to succeed in anything, especially in science, become a professional in something. Choose a subject, but be a professional. And today, high school students can become professionals because information is available. It's available to everybody. Become a professional, and it will carry you a long way into the future. Be a professional. And then you can believe in yourself. And then also you have to have courage. I was early in my academic career, and some people liked me in my department, other people did not. And it was not easy to stand up and walk tall under certain circumstances. So we have to have courage. I was really worried that my promotion will be impeded dramatically because Linus Pauling said that I'm talking nonsense. Okay, so we have to have some courage. You may have other answers, but that is mine. And so thank you so much for listening to me.